Hello, I wanted to establish a connection in your minds between electromagnetics and optics. Like, how do we get from everything we've been talking about to optics? They're not unrelated, although they may seem like completely different topics unrelated, they are connected. So I want to just remind you some of the conclusions we came up with in talking about electromagnetics. One is that by running a current through a wire, which is basically the motion of electrons, motion of charges, we create magnetic fields. So motion of charges creates magnetic fields. We did that with a solenoid, we did that with a piece of wire. If you put charges through there, you're going to get magnetic fields that start to exist around them. The other thing that we learned is that changing magnetic fields, or changing flux, which can be created by a changing magnetic field, but a change in the magnetic field results in, I'll say, a change in flux, which can result in an induced, it's called an induced electromagnetic force, or voltage, basically, which is really a voltage. Remember, where you have a voltage difference, a potential difference between 2 points, you actually are generating an electric field. So change in a magnetic field is actually producing an electric field, but just like the voltage changes over time, if the magnetic field keeps changing, unless it's changing in a uniform fashion, but if it's going, say, higher and then lower, then higher, then lower, you're going to get your voltage also going higher and lower and higher and lower, which means that your electric field is going to be going higher and lower and higher and lower. There's a minus sign that relates the electric field to the changing magnetic field, so when this is higher, this goes lower, and vice versa. But what I'm basically saying is that a changing magnetic field creates a changing electric field. Similarly, and this isn't something we've talked about, but when you get a changing electric field, all of our electric fields that we've talked about have been constant, but when you get one that changes, that actually produces a magnetic field. So in other words, changing a magnetic field produces an electric field, changing an electric field produces a magnetic field, and you go back and forth. And so if you can start to generate some sort of a changing something, such as an electron, let's say you have an electron here, and you can get that electron to oscillate at some frequency here, well, that is basically creating a changing, well, it's creating both a changing electric or a changing magnetic field, depending upon how you want to look at it. But one creates another, and what you get then is an outgoing disturbance that propagates as the electric field and magnetic fields change from one to another. That change propagates outward. So while the electron's still doing its thing here, that change is propagating outward. For that matter, if the electron decided to stop doing this thing, that change is still going to be propagating outward forever. Of course, it's going to become, because it's basically propagating outward on a sphere, the bigger the sphere is, the weaker the electric and magnetic fields are. But it's basically going to propagate out forever along that sphere. That is called an electromagnetic wave. You may say, what's an electromagnetic wave? Well, you see them all the time, or you hear them all the time. Well, you see them all the time. Light that you see is a propagating electromagnetic wave. Radio waves that your radio can convert into sound, those are electromagnetic waves. So what's the difference between light waves and radio waves? It's just the wavelength. They're all electromagnetic waves that obey the same sort of properties. Even some of the ones you started to see last week involving refraction, reflection, all that kind of stuff. Those are properties of electromagnetic waves that either radio waves or optical waves can exhibit. They'll exhibit in different ways and on different scales, but they exhibit the same sort of phenomenon. One little thing I'll add to you, we've been talking about epsilon zero, That is the permittivity of free space. And that has a value of about 8.85 times 10 to the minus 12th coulombs squared per Newton meter squared. So the permittivity of free space, as I mentioned, is 8.85 times 10 to the minus 12th coulombs squared per Newton meter squared. And the permeability of free space, mu 0, is 4 pi times 10 to the minus 7th Tesla meters per amp. And it turns out when you do what I did in terms of talking about the change in electric field producing a magnetic field and the change in magnetic field resulting in an electric field, and you actually solve the related differential equation, kind of like what we did at the beginning of semester when we were talking about waves, that's when you get the electromagnetic wave. And one of the solutions to the electromagnetic wave comes up with, we solve for something that turns out to be the speed. The speed of the wave, which I'll call c, is equal to 1 over the square root of mu 0, epsilon 0. And I will challenge you to calculate that, and also to check its units. It will have units of speed, with all the units that I gave for epsilon 0 and for mu 0. If you multiply them together and take the square root of them and invert that, you will get meters per second. Believe it or not. Try it and see. If you take the two values I gave you, multiply them together, take the square root of that, and take the inverse, you will get the speed of light. You say, whoa, how did that happen? Well, the speed of light is a function of the permeability and the permittivity. When you think about it, the speed of light is a function of changing electric and magnetic fields. So they're going to be influenced by these two quantities. So we talk about in optics some materials being optically dense. Well, they'd be optically dense if these quantities are slightly different as a result of the relative permeability or the relative dielectric constant, which we talked about earlier this semester. So that can change the optical density of the materials, which can make the speed of light be a little bit slower in those materials. So if you have material with a different relative permittivity or permeability, that will affect the optical density. So the speed of light, which is approximately 3 times 10 to the 8th meters per second. But you can check it. Try this out. Okay, so in subsequent videos I will talk just about the optics, but know that when we talk about the optics, the electromagnetics that you've been learning about is included in that discussion. It's part of it.